Okay, we're picking up where we left off in section 1.2. I was planning on finishing this section in the previous video, but we'll go ahead and finish it here. So, okay, we've talked about some of the main tools that are used in geometry. So, a ruler and a protractor. A ruler, with a ruler you can draw straight lines, but also rulers have scales on them which allow you to measure the lengths of lines or line segments. Okay, the protractor allows you to measure angles. Okay, and now another tool that's commonly used in geometry is a compass, as shown here. A compass allows you to draw circles or portions of circles, which are called arcs. Okay, so here's a circle, but then you can see there's a portion of a circle that's called a circular arc. All right, now this is the 21st century. We have computers, and computers have these, naturally built-in compasses, right? So here's the compass tool within the software I'm using, and so you can move the center point wherever you want. You can change the radius of the circle, but you could also make this as like an elliptical tool. You can make this an ellipse. And so I'll make an ellipse here, and then you can just come to the outline and draw a portion of the ellipse or the full ellipse, like that. But I could obviously also come back and set this to, it gives you a gauge here where I can tell if it's a circle. So that would be a circle. And I can change the size, and I could draw a circular arc like that, and just leave that, or I could do a full circle, whatever I want to do. And when it comes to actually with a compass, if you're drawing on an actual piece of paper, in the next video, I'll either at the end of this video or the next video, I'll give a demonstration on this. But the idea is one end is just like a pointed piece that the purpose is that it sticks into the paper, and so it doesn't move. It stays at its position. That's the center point that you want the circle to be. And then the other end has a pencil or a pen in it, and you can adjust this so you can get the radius you want, and then you screw it in to tighten it in so it doesn't move, and then you can draw your arc or your full circle. Okay, now one thing to note though is it's not like if you see any curve that means it's an arc. So, is this an arc? It might be. I'm not sure, but the idea is, so, okay, if I make an ellipse and I draw, so I'll put this, okay? That is not an arc. I don't know what the technical term for that would be, a spline, just a curve. That is not an arc. An arc has, if you see a curve like something like this, a curve, and you want to know is it an arc, remember an arc is going to have a radius and a center position. But you're not going to see it, but you could visualize it, or you could come up to an arc and draw its distinct center point and its distinct radius. You can't do that here. So just to show you, let me come back to a circle. Okay, you can't. Well, that's not the. Well, I mean, it's pretty close. Usually, this isn't the best example, but for this entire curve as a whole, I can't create any size circle that will line up on this. I mean, that's actually pretty. Again, that's pretty close, but the radius is changing. You could break this up into. You could break any curve up into individual pieces and create this, and it's like a combination of arcs. You can do that, but this as a whole, I couldn't line up with any circle of any radius. I could adjust the radius of the circle and the center position. I couldn't get this as a whole to line up. But yes, I could come to like here and say, okay, that portion of this portion here has center and radius this, and then kind of line this, maybe change the radius a little bit, line this up here maybe, and say, okay, now this piece of it has this radius and this center position, and kind of see what the combination of the curve is as a whole. It's combined of a bunch of arcs. But as a unit, as a whole, I can't, this is not an arc. You know, I can't, okay, I can get that starting, the start of it to line up, but then the end, it veers off. Maybe I make it bigger, move the center position. All right, maybe let's make it a little bit bigger, maybe. No, now it's veering underneath. See? Okay, now if you want to have a specific radius of circle, well, with a computer, I guess you could type it in, but I mean, I don't know how you interpret an actual length on a computer screen. But, you know, in real life, what you would, the idea is that you would bring in a ruler and then put the center position, you know, at 0 or wherever. And then, so let's say I wanted this 5, whatever 5 is. There's the radius, and so now, there you go. This is a circle. There's the radius, and there you go. This circle has radius of 5. All right, the ancient Greeks insisted that only 2 tools, a compass and a straight edge, be used for geometric constructions, which were idealized drawings assuming perfection in the use of these tools. The compass was used to create perfect circles and for making off segments of equal length. The straight edge could be used to draw a straight line through 2 designated points. Okay, a circle is the set of all points in a plane that are at a given distance from a particular point, known as the center of the circle. The part of a circle between any 2 of its points is known as an arc. Any line segment joining the center to a point on the circle is a radius, plural radii, of the circle. Okay, so yeah, this is an important paragraph here. Let's go through this slowly. So, what is a circle? What exactly is a circle? It's the set of all points in a plane that are at a given distance from a particular point known as the center of the circle. All right, so what do we notice? What can we notice here from this definition? Well, okay, the first thing is that the center is not a part of the circle. The center point of a circle is not on the circle. That's not a point on the circle. That's just a part of the defining characteristic of the circle. The circle is the set of all points that are the same distance from this special point called the center point. Okay, so that's a good trivia question for somebody. You know, is the center of a circle part of the circle? Technically, no, because a circle is it's a set of points. That's what a circle is. It's a set of points. So the circle is those points. So, and all those points are a equal distance from the center point. Why isn't, okay, think about another way to look at why the center of the circle isn't on the circle. Because if a circle is the set of all points that are a fixed distance from a certain point, well, the center is distance, the distance of the center point from the circle is 0. Well, that doesn't satisfy the criteria of the definition of the circle. All of these points are the exact same distance from this point here. So I can't say that this point in the middle is on the circle because it's not the same distance as these other points are from that point. You see? Okay, what else? Similar to how we talked about a line was an infinite number of points, so is a circle. Why is that? Because there's an infinite number of points. You can pick any 2 points on the circle, no matter how close, and there's going to be a point in between those points because I can get, no matter how close, if I went a trillionth of a millimeter along the circle away from this first point, well, I can go 2 trillionths of a millimeter from that same point. I'll be in between the first point that I picked. Okay, and then similar to we talked about this with triangles. But, everything we've talked about so far, well, I don't want to say that. For an angle, this is the case. A triangle, this is the case. A polygon, this is the case. And a circle, this is the case. That it says, so a circle is the set of all points in a plane. In a plane. A circle is contained in a plane. Just like a triangle is contained in a plane. Just like any of most of the two-dimensional shapes that we're going to discuss in this course are contained in a plane. But I hesitate to, I don't want to go too far with that. We'll talk about this more as we go through the course, but you wouldn't say a line is contained in a plane. No, a line is not contained in a plane. A line can, yeah, you wouldn't say that because, okay, let's think about 3D space. All right, you can define, there's an infinite number of planes in 3D space. Okay, yeah, you have the ZY plane or the XZ plane or the XY plane, sure, and you can think about your computer screen like the ZY plane, but you can make any plane anywhere. There's a plane, or you could, you know, right, there's a plane. And so any circle or triangle or angle is going to be contained in a unique plane in 3D space. So every time you see a circle, I guess not in your textbook, but like anytime you look and you see a circle at an amusement park or if you're whatever you're doing in the woods, when you go hiking, whatever, if you see something that's a circle, you can think about, well, that's contained in its own plane. You know, this is beyond the scope of this course, but as you get into, we really go through this more in multivariable calculus. Well, we're going to learn about the geometry of 3D space. You'll get a sense of how you can actually, define, get the equation of a certain plane in 3D space. You can put numbers to that. So you could you could look at any circle that you see in life and think about, okay, that's also in its own unique plane in 3D space. And if I established an origin of a coordinate system somewhere, a 3D coordinate system, I could actually write the equation for the plane that circle is in. So a circle is going to be in a plane in 3D space. So is a triangle. Any triangle. So is any angle. Why? Because an angle is, what do you need for an angle? You need two straight sides. So that creates a plane, a unique plane. But when it comes to like a line, you can't define a specific plane that a line is in, because I could have, you could get an equation for a line in 3D. Let me make this. You can get an equation for a line in 3D, but okay, the line could be in this plane, but it could also be in this plane. And the reason why this happens is because a line is one-dimensional, whereas a plane is two-dimensional. And so the flat objects, like, it's anything that's two-dimensional is going to be contained in a plane, like a circle, a rectangle, a polygon, a triangle, an angle. An angle is two-dimensional because you've got these two sides that are in their own distinct orientations. So I guess if you have an angle of 0 degrees, that's a line, so that's not a plane, but in a general angle, okay? And so again, the circle, if we come back to the definition of a circle, it's the set of all points in a plane, and all of those points are a specific constant distance from a particular point known as the center of the circle. Now, the center of the circle is obviously enormously important for a circle. I mean, saying the center is not a part of the circle is confusing, because if it's not a part of the circle, then it's a blood relative of the circle. You know what I mean? But it's just a location in space. It's not even a point. Like it is a point, but and it's not a point in the sense of you have the points on the circle, right? Those are all points, but this is just a location in space. It's not even when you're thinking about, because we're talking about the circle is the set of all points, so I don't want to call it a point. But it's just it's a special location in space that is intimately related to that set of points. Okay, the part of a circle between any two of its points is known as an arc. Yeah, between any 2 points of a circle, the portion that's between those is an arc. Any line segment joining the center to a point on the circle is a radius of the circle. So, yeah, notice that what they're saying about the radius is that you join a point on the circle to the center. So I can't say this. That's not a radius. I've got to join a point on the circle to the center. And that's known as a radius. And you can think about the radius is going to have a constant length because by definition of the circle, if all of the points are the exact same distance from the center point, and we're calling a radius is any line segment that joins a point on the circle to the center, well, it's going to be constant by the definition of the circle. Okay, construction 1, which follows, is quite basic and depends only on using arcs of the same radius length to connect line segments of the same length. The arcs are created by using a compass. Construction 2 is more difficult to perform and explain, so we will delay its explanation to a later chapter. Okay, so let's see. Construction 1, to construct a segment congruent to a given segment. So given segment AB in figure 1.26A. Oh, okay, here. Construct segment CD on line M. So that segment CD is congruent to segment AB, which means that the length of CD is equal to the length of AB. Yeah, so you would just get a ruler, measure this length, and draw that same length here. So construction 1, which is quite basic, it depends only on using arcs of the same radius length to construct line segments of the same length. Okay, so what's the second part? With your compass open to the length of segment AB, place the stationary point of the compass at C and mark off a length equal to AB at point D. Okay, so what are they talking about here? I guess they're saying that, so you don't have to measure this with a ruler. You can take your compass, adjust it, put the stationary point at A, adjust it to where the pin is going through B, and then tighten down the screw, and then now pick up the compass, put it at point C, the stationary at point C, and then draw the same location. So now you have equal lengths. That's instead of using a ruler, you could do it this way. It's just another way of constructing using a compass instead of using a ruler, you could use a compass to create a segment that's congruent to C to AB. Okay. Yeah, because you've drawn I guess the idea they're going for here is that you've drawn a tiny portion of an arc here, right? Yeah, I think this is what they're going for. You've drawn a tiny portion of an arc here, a tiny portion of an arc here, but you fixed on your compass, you fixed the radius. You set your compass equal the radius of your compass equal to the length of this line segment, and then you tightened it in and fixed it. Well, the radius doesn't change, so you just come here and you could you don't have to you could put your center point wherever you want, and they drew this line M for you that was oriented straight across with this line segment, so you just put your center point fix it in on the line segment, and then draw an arc, and then there you go. The radius was fixed on the compass. Okay. The following construction is shown step by step in figure 1.27. Intuition suggests that point M in figure 1.27C is the midpoint of AB. Okay. To construct the midpoint M of a given line segment AB, so we give this line segment AB, we want to construct the midpoint M. We're going to do this in like a roundabout way. You could just measure this, right, with a precise ruler, but so given segment AB, construct the midpoint on AB such that the length of AM is equal to MB, right? So to do this, figure 1.27A, open your compass to a length greater than 1/2 of segment AB. Okay, so, like the radius would be from A to here, let's say. It's greater than 1/2 of AB. Okay, well, we're starting up here actually, so you know the midpoint's somewhere around here. So fix the compass here, the fixed point, and then make the radius something out there where for sure it's greater than 1/2 the radius, and then tighten it in. Okay, now using A as the center of the arc. Mark off an arc that extends both above and below segment AB. So, okay, you take A, you fix the center at A, and then draw this arc. Because we made the radius bigger than the half of the length of AB, so you can draw that arc. And then they're going to say, I'm assuming, then you fix the center point here and do the same thing. We're not changing the radius of the compass, though. All right, and now we've got these 2 points C and D where the arcs cross. Now draw segment CD, where CD crosses segment AB is the midpoint M. So yeah, that's pretty cool. So they do this. And there's the midpoint. Huh. So why does that work? Interesting. They said here it's more difficult to explain why this works. So the construction 1 worked because we're using arcs of the same radius length to construct line segments of the same length. Yeah, because we fixed the radius of the compass. So you know that if we fixed the radius of the compass to be the length of the first segment that we were trying to make a congruent segment of, so I might not have explained this right. It's like you would have to, if I'm trying to make a line segment that's congruent to AB. So, you took the compass, fixed it at A, and then made sure you fixed the radius to where it went through you fixed the radius to where you could draw an arc that went through B. Okay, that means you have a radius set to the compass that's fixed, tightened in, that's the length of AB. Next, you can draw a line however you want, but you have to draw a line first. In any orientation you want. Doesn't matter. Then you take any point on that line and you put the pin, the fixed, the pin point of the compass, the center point, into that point. Then you just draw an arc, and where it crosses through the line, then that's where you're gonna have the congruent line segment with equal length. But you couldn't think about this though. You couldn't do this without drawing a line first and just take a point, fix the compass in, and then draw an arc. Why wouldn't that work? Well, because where on this arc, I can't just arbitrarily connect this point to the arc. Would this line be congruent to the original line? I don't know. I don't know. Well, actually, no. That's completely wrong. Yeah, it would be. Yeah, it would be. It would be. You can take. Yeah. What am I saying? You don't need to draw a line first. Your radius is fixed. What you could actually do is pick up any point you want in 3D space. Your compass radius is fixed, and then just draw a circle. And then you can pick any line you want that connects the center to the radius of the circle, or the center to a point in the circle, and that is congruent to the original line. Just because they're not in the same orientation doesn't mean they're not congruent, right? You can reorient the shapes however you want, as long as when you line them up, there's a perfect match. So yeah, you didn't need to draw a line first. You see where I messed up? I was thinking that you have to draw the line first, because once you draw the arc, then how do you know where to connect the original point to the arc? It doesn't matter. This line length is the exact same as this line length, and that's all that matters for making a congruent line segment, is that the line segments need to have the same length. Okay? But now coming back to construction 2, it's more difficult to explain, so they're going to explain later, but can we think through potentially right now, of why this worked? Well, okay. We know that with the radius fixed on the compass, we know that the distance from point A to any point on this arc is going to be the exact same as the distance from point B to any point on this arc. Okay, I'll say that again. We know, since the radius of the compass was fixed, that the distance from A to any point on this arc is going to be the exact same as the distance from B to any point on this arc. Okay? So, therefore, where those lines cross, or where those arcs crossed, we know that the distance from A to C is the exact same as the distance from B to C. And the distance from A to D is the exact same as the distance from B to D or D to B. These distances must be the same. And so I guess now with the symmetry of that is going to mean that this line is going to cut I guess the two diagonals of this, I guess I don't know if that's a square or what, are going to bisect each other. Yeah, we'll be able to prove that this is true later, but it's something to do with the symmetry that set up. The fact that AC is equal to BC and AD is equal to BD and all those four are equal, that symmetry dictates that those diagonals are going to like bisect each other. So yeah, we'll learn that more officially later. Okay. Example 7 in figure 1.28, point M is the midpoint of AB. Find the length of AM if AB is 15. Well, that's just 15 divided by 2. Find length of AB if AM is equal to 4.3. It's 4.3 times 2. Find the length of AB if AM is 2x plus 1. All right, well, if AM is 2x plus 1, it's just 2 times that. 2 times 2x plus 1 is 4x plus 2. But there's a variable in it. You're saying that AM is not set yet until you pick an x. So once you pick if I said that, okay, x is going to be 3. Okay, so that means that the length of AM is 3 times 2 is 6 plus 1 is 7. So the length of AB is 14. All right, the technique from algebra used in example 8 and also needed for exercises 47 and 48 of this section depends on the following properties of addition and subtraction. Okay, so yeah, we talk about this in detail at the beginning of the algebra course, which is like the pre-algebra section, properties of real numbers. But all right, if A is equal to B and C is equal to D, then A plus C is equal to B plus D. Equals added to equals provide equal sums. Well, yeah, of course. I'm not sure what they're... If you said A plus C, if you had A plus C, okay, and you also had B plus D, but A is equal to B and C is equal to D, well, then of course they're equal. And same if you subtract them. If I have 3 plus 1, but then I have another number that's equal to 3 and another number that's equal to 1, I add those up. So, yeah, I'm not sure what... Seems kind of trivial, honestly, but I guess from a technical math perspective, this obviously isn't trivial. But yeah. All right. Figure 1.29, point B lies on segment AC between A and C, okay, but it's not necessarily the midpoint. If the length of AC is equal to 10 and the length of AB is equal to 2, is 2 units longer than BC, find the length X of segment AB and the length Y of segment BC. Okay, so let's see. Let's write down some of the things that we know. All right, we know that we can see clearly that the length of AB is equal to X, the length of BC is equal to Y. Okay, so yeah, I guess we can start there. Even though that seems obvious, but let's start there. So the length of AB is equal to X, the length of BC is equal to Y. Okay, now the length of AC is equal to X plus Y. All right, now they give us the length of AC is equal to 10. So X plus Y is equal to 10. Okay, now they also tell us that the length of AB is 2 units longer than the length of BC. So the length of AB, which is X, is 2 units longer than the length of BC. You see? So you take the length of BC, you add 2 to it, you get the length of AB. And so now we have 2 equations and 2 unknowns. Now I think that's what they were going for here with these properties of how you can add equations together. Yeah, we talked about this in algebra chapter 5 with the multiple equations and multiple unknowns. It is kind of confusing to think about how you can add 2 equations, but the idea is, so if we do X plus Y is equal to 10, and then line that up down here, we can subtract Y from both sides, and we've got X minus y is equal to 2. Okay, we can think about the idea of adding, we can add or subtract these two equations. What does that mean? How you add or subtract two equations? The idea is like, so okay, let's add these two equations, because then the y's will subtract out. The idea is, it's like, okay, I'm going to use the equivalence property for equations. I'm going to add the same thing to both sides of x plus y is equal to 10. Okay? That's what I want to do. I want to take x plus y is equal to 10, and I'm going to add the same thing to both sides, and as we know, that doesn't change the equation. Okay? Now, but what am I going to add? I'm going to add 2 to both sides. I want to add 2 to both sides of this equation. Okay. Well, let's come to the right side. 10 plus 2. There we go. Okay. Now, am I going to do on the left x plus y plus 2? I could do that, but why don't I do x plus y plus x minus y? That's also equal to 2. You see? And I think that's what they're going for here. That's also equal to 2. X plus y plus x minus y. So I just added 2 to both sides. And that's the idea of adding or subtracting, two equations. I could have done this. I could have looked at it the same way, saying I'm going to add or subtract 10 to both sides of this equation. Now, instead of doing it, that way, we just line the equations up vertically and add them. So x plus x is 2x, y minus y is 0, 10 plus 2 is 12, so x is equal to 6. Now, okay, x. Let's see, we have 6 minus y is equal to 2. Y plus 2 is equal to 6. Y is equal to 4. And there you go. There's the length of A, B, and BC. Okay, and now I think we'll go ahead and work a few example problems from this section. As I've mentioned, for this opening chapter, we're not gonna be doing too many example problems on these definitions and proofs that are more for math majors. For non-math majors, we're going to focus on more of just the pure geometry, but I think this section we might work a few examples.